So let's go. Hello, everyone, again. Welcome to the 1, 2, 3, I think 5th session of the bootcamp, deep learning bootcamp of this winter. This session, we are talking about NLP. We are extending over the concepts that we saw in the previous week, including RNN transformers and all of this. But for some of you might be, I think some of you are also online and some people here were not here the previous week. We'll do a very, very quick recap, but then we will directly go over topics that are interested for today. I hope it won't take long. Maybe it will be a bit longer than the past 2 sessions, but we strive to keep it a bit short and also with a gap in between. With that said, let's go. And if you have any questions, raise your hand in the middle or write in the chat, as always. Chat for people online, of course. So this slide is super boring for you, so I want to explain it again and again. But the idea, as we just saw, is that we had the deep neural networks that had some shortcomings. We still use them in the end of other architectures, but we tried to add new abilities by adding functionalities or features before them to act for feature extraction, such as what we did with CNNs, that we had the basically convolution layers and all of those to process the data and extract features before getting to the layer. And that's what we also seen with RNNs and transformers as well. So if you remember, we discussed the task of time series, which was data that was measured at regular intervals or step by step, like a stock price of a company or answers of a student to an exam. And importantly, also a written text. We said, this is basically the focus of today, right? We said we can model a text, a sentence, or a paragraph, or a document as a time series in which each word comes at a specific position of time. And we can do different tasks. For example, we can classify the sentences, classify the documents into a set of different categories. We can say this text is a happy text or sad text, or if it has a grammatical error or it doesn't have a grammatical error. So all of these are basically classifying a set of words that come after each other, which we can model as a time series task. We can also forecast or do predictions, like what is the most likely word that comes in the end. And we will see examples of both in today's lecture. So basically, just as a recap, this is the task of time series, and we are modeling the text as also a time series data. All right, if you have any questions, just let me know. We saw recurrent neural networks that were one of the first good solutions to tackle time series data. We put input to a set of cells. Each of them had an output and a hidden state passed to the next cell. And this could help us could help the network have an inside memory to be able to find patterns in the data, which is important for time series. Each output in a sequence of RNN cells depended on every input that came before that, or the same input. For example, here H0 does not depend on X1 because there's no connection from X1 to H0, but it depends on X0. But however, the last one depends on all of the inputs because all of them are indirectly related to the output. And that's what we saw. We said that we could model a lot of time series with RNNs and also text, but they had a lot of shortcomings. I will recap the shortcomings also in a bit. So this was the general architecture of the RNNs as we saw. We saw for a lot of problems such as vanishing gradients, which was a problem when we want to take care of elements that came way past in the sequence due to multiple usage of the chain rule. We had basically the gradients were all exploding or converging to zero, not enabling the model to be able to learn from the data. So we saw one solution to this that was suggested by researchers called the LLMs that added one extra layer, basically one extra layer of transferring cell state between cells so that the problem was mitigated, not solved, but mitigated. But we saw that there are also a lot of downsides with LSTM. For example, they are computationally expensive, and they also have the same basic shortcomings of RNNs as well because they are just an extension. So this is we are not going to use them today. We are focusing on transformers today, but just as a recap. The important thing about today is the concept of sequence-to-sequence models that we saw. This was a concept that we saw on Friday. So some of you and you people online were not on Friday, so I'll just give a recap. Imagine we want to translate a sentence to another sentence. We said that each word in the translation does not only depend on the corresponding word in the source, because the order of words can change when you are translating, for example, from French to English. The adjectives can come after the noun, before the nouns, and so on. So instead of just getting the output of each cell, researchers had an idea to design a sequence-to-sequence model by which there are a set of encoders that are just normal RNN cells. We input the data to each of the encoders, but we don't care about the outputs. We just take care of the output of the last encoder and use it as an input to another set of RNNs. Each of them is a decoder. And then for each decoder, we see the output, and that will be our result. By this way, all of the decoders have access to all of the input data. And so, for example, for the task of translation, each of the decoder knows the whole source sentence so that it can provide the correct translation, even if the corresponding word comes later in the sequence. And you can also play with it, like play with how many encoders and decoders are there, and a lot of things. Still, the order of the data is preserved because there is this connection between the RNNs. So we saw there is one big disadvantage of this model, in which that all of the inputs should be compressed into one vector here. And from that one vector, we should generate all of the output again. And this is very, not unnecessary, but this is not useful for us, because usually, specifically in long documents, it's very difficult to compress them into one vector and then again decompress them such that no content is lost. Here we have a big content loss because we are compressing a big sequence, which can be very much larger number of encoders just into one vector, and then using that one vector to decode everything. So it depends on how much data is there, but it's usually not very efficient to work with the data from this because you have a lot of data. It's fine, right? I think we all saw this. And there was also there are also another problem as well. For example, this is not very efficient to calculate in parallel, and like problems like that. To fix the problem of, we saw that to fix the problem of compressing everything into the final state and then using that final state to decode everything, researchers have came with the concept of attention, by which each RNN cell in the decoders gets as input a weighted sum, or basically a formula of all of the outputs of the RNN cells in the encoder. So by this way, we don't have the bottleneck of compression into one vector, which is nice, but still the sequential architecture here doesn't allow us to do stuff in parallel because each of them depends on the output of the previous one. So we need to first do all the encoders sequentially, then you have the state, and then you have to again do all the decoders sequentially. To fix this problem, and also to fix more problems, researchers introduced transformers, which basically remove the whole recurrence and just put a set of feed-forward neural networks here, then states, and then the attention layer. So we had two attention layers here, one for the encoders and one for the decoders. I won't go to the details again. If you want, just watch the transformer lecture again, or just read more on the internet or everywhere. But this is the basis of our models that we discussed today. We are discussing about transformer models in which we have encoder blocks that have a set of neural networks that basically get a somehow weighted sum of the input tokens. Then we have some internal states, and then we have a decoder block in which gets all of the states, and by a weighted sum would generate the output for us. So we have the encoder and decoder, and this can do any kind of sequence-to-sequence task that we want. For example, generating a translation. We said that we don't necessarily always need to both have the encoder and decoder. You may say, how? How does that make sense? We will see today. But we don't necessarily need to always have both encoder and decoder. Any questions on the recap? Fine. All right. So for you who just joined, we just did a recap. So if you saw the previous lecture, it should be fine. And we saw that in transformers, also, there are some minor components that we won't go into depth today because we don't need necessarily, like the normalization that we do here. But importantly, we have the positional encoding, because in RNNs, we had the sequential or recurrence, but in transformers, we don't have it. So we should somehow keep track of the order of the items that come in the time series sequence. So for that, we add a positional encoding to each element before giving to the transformers. That was all transformers, right? So now with this architecture, and basically with the code that you might have for transformers, you can just give it a time series data, and it would try to predict it like an RNN architecture would, maybe even better. Albeit it needs more data. However, when we want to apply to domain of text, like for NLP, which we want to like do natural language processing and we want to process text, there are certain things that we need to keep in mind, both in the architecture and before using the architecture. And those are the main things that we'll cover today. So first, we will see how should we provide the input to this model, because our text, our natural text are a set of words, but here we need vectors, so we need to somehow convert them. First, we will discuss this in the first half, and the second half, we will see two famous architectures, which are basically adaptations of transformers that prove to be very useful for textual data. So, with that said, let's go. Any questions? All right. Perfect. So, let's explore NLP as a specific deep learning task. Natural language processing, I mean, you know the definition, but it is basically any task that works with textual data. That's it. So imagine you have a model classifying if a certain sentence is happy or sad. Or for example, you are running a blog and you want to do content moderation and to check if each of the sentences that users write is valid or not valid, or anything like that. You want to classify a sentence. For such a model, if we want to make it as a deep learning model, of course, like any type of model, we need different components. We need the model that gets the word as input, and we also need to have a mapping between the model outputs and predictions. However, we also need to represent words in a way that's understandable by the computer, because the words are our natural language, and we have to convert them into a vector format that is useful for the computer and that model can train on. You already know 2 and 3. The model that gets the word as input is basically a transformer model here. And mapping between the outputs and the predictions is also easy. You learned about softmax, which is a function that would convert the outputs of the model into probabilities. And thus we can convert the output of the model to see which word is most likely to come after, or which class is the most likely to be the class of this sentence. And we can just use softmax to do the prediction. So you already know 2 and 3. I mean, we will also cover it, but we now want to first focus on 1. How can we represent words of a text in a computer understandable way? Or as we call it, how can we represent words in terms of embeddings? Is the term that we usually call it. So any questions? Fine. Perfect. So let's go. First of all, we have a sentence that is usually long, or we have a document. We need to first, even for a human, convert it to a smaller chunks, and then try to convert each chunk to a computer understandable way. Because you can't convert a whole text into just one vector, right? So you should first try to chunk it in a way so that the units, you convert it to its units, and then we can think, how can we convert each unit into a computer understandable way? We call this process tokenization. So what's that? If you don't know, again, many of these topics might be boring for some of you, so I will cover it because that's it. Each sentence in our natural language contains several words, right? And in real language, we may split sentences by words. Here, we call them as tokens. We call each token a meaningful unit of a set of characters. For example, I am attending the summer bootcamp. It's actually, I should change it to winter. It's an example from summer. Consider this summer. I'm attending the summer bootcamp. Each of the words in this sentence could be one token. I am attending the summer bootcamp, and maybe the exclamation mark, you can also consider it as a token, right? So this is a way of converting a longer document to a set of chunks, and then we just need to somehow convert each of them to a vector. And then we have the problem solved in a sense. Because as we said, each text is a time series, and the words are coming time after time. And so we just need to split it into the units, which we call tokens. This is a type of discretization, which is important for our discrete models, like the language model that we will see today, to work. Fine, right? So we are just converting two words. However, do you think is this the only way to tokenize the sentence above? And if not, do you have any other ideas on how can we convert the sentence to a set of tokens? Any of you has an idea? Like, do you think this is a good way of tokenizing it?
You can separate words into like components, like bootcamp.
Exactly. So that's something. You can separate words into components. It's good sometimes and not good sometimes. Like, for example, some words, if you separate them, they mean something. Like, I don't know, like maybe is there a compound word that you separate it means something. Imagine it was like, I don't know, like meaningful. Maybe even if you convert meaningful to meaning plus full, it means something because it means that you are talking about the meaning of a thing, right? So sometimes it's useful. Maybe for bootcamp, it could actually harm because bootcamp does not mean anything regarding boot. Boot is a different word, but it's a valid idea. And actually, that's what I wanted to say. Also, another thing is that here, consider word attending. Also, if you had another sentence that said, I attended the summer bootcamp, not I am attending, it would say I attended, you would still say that it is generally the same meaning. So it would be also nice to split the suffixes or the prefixes of the word, like convert it to attend plus ing, so that we find, because here I know attending is a word, but actually the meaning is attend. And the ing is just a grammatical feature added to the end. Or also in French, you have a lot of suffix that you add in the front of the verbs, actually, I think more than English. So these are all the things that could have happened. Or imagine I am was like I apostrophe M, like I am, concatenated together. It would be a good idea to separate it because I has a meaning on its own and am has a meaning on its own. So as you might have guessed, tokenization is not an easy topic. Also, if you tackle new languages, it could be even more difficult because you need to learn how in that specific language the words and the compounds are being made. So, there are some examples actually here. Like imagine someone wrote checking as one word. Here it means to separate it, right? Check plus in. Or like if you're 6 years old as one word, it makes sense to split 6 years and old, because here there is a meaning, like 6 years old is 1 year younger than 7 years old. But if you consider it as one word, you don't have any sense of what it means. It's just that when you compare it to separate words that you think, okay, 6 years old means it has been 6 years since they were born. So you should basically convert some words into the subsets such that the computer could better understand the meaning of words. We as humans love to connect words together, but computers don't. Again, attend and attending. They aren't, so if we do a splitting only by spaces, like if you write in Python text.split and then put a space, attend and attending would be totally different tokens. However, they are super close. They just have a difference in grammar. Also, not only there is the problem of meaning, but if you consider each of these variations of grammar as another word, the number of possible words increases a lot for each variation. And that's very bad for computational issues, because the more you have words, you will see later that it's basically more difficult to manage all the data and everything, like the computation of the models and the time that they take to run, and everything is worse. So we try to reduce the number of words that we have by splitting them to the components. All fine? You got the idea, right? If I speak, yes.
Excuse me,
Yes.
like how do we know if a tokenizer is good? Like for instance, we cannot check all of the words, right? Like and checking their meaning, like attend and ing, if it's correctly tokenized and everything. But like is it like, I don't know, how many tokens per word do we need, like to say that this tokenizer is good enough?
That's a very good point. So there, we can't say how many tokens per word do we need, because a lot of words are just really one tokens. Like, I don't know, like attend, I don't think you can convert it to a smaller word. If you do it, it would be even more meaningless. So it's not a good idea to put a criteria on, I want each word to be split into n number of tokens. What a lot of people do in practice is they train a model, like they do the whole thing that we will see today with a tokenizer, and if it works, then it works. So that's maybe a weird idea, but if in the end a tokenizer is useful to help our models in the accuracy of the models in the end, then it means that it's doing the tokenization well. Actually, you may have seen, I will cover it later, but you may have seen this example. They asked ChatGPT, how many letters does this word have? Like they say, I think the famous example is strawberry. They say, how many R's does the word strawberry have? And it always fails, at least used to fail. Those are all problems that come from the not proper tokenization. So you can check it later, post hoc, basically after training the models, but I don't think anyone has said that you should have n tokens per word to make it useful. At least I haven't seen any suggestion for the count, I have to say.
So we just can't estimate tokenizer without like doing some
I
empirical
don't
trading.
think so. Like, yeah, you can look at the outputs and see if they make sense. Like, if the words that have been splitted have meanings, but I don't think there's a quantitative measure, at least on top of my mind, other than continuing using tokenizer in a model and then see what happens. Like for itself, I don't think there's a very good quantitative measure. It's just looking at the data and qualitative as far as I know. Yeah.
Okay, got it. Thank you.
Perfect. But yeah, there are a set of rules. Like, for example, they always say use the exclamation mark as another token, because the exclamation mark, question mark have meaning on their own. It means that the sentence is a question or the sentence is surprising, right? And also, you need to take care of languages that might not use a space as English does. Like some Eastern languages might be different. Sometimes you need to take care of a specific tokens that might be needed if a user has a typo and it doesn't match any token in your list. Maybe you should put an unknown token or this kind of a specific token. There are a lot of considerations to be made here. I just wanted to give you a heads up on the problem of tokenization, which is a research field on its own, at least used to be. And still some problems that ChatGPT and these models have might be rooted in the tokenization process. So it's not a solved problem, but yeah. What we usually do it now is there's a list of the suffixes and prefixes and just split them. And then we split everything else by a space. Yeah. So that's another example of tokenization that might be. Okay, let's go. We call the set of all possible tokens the vocabulary. So when you hear the term vocabulary in the context of LLM, it means the set of all possible tokens. Like basically every word in English, not every word, every subword in English or in any other language, but every subword. For example, the word bootcamp might not be in your vocabulary, but boot and camp might be if you are splitting bootcamp. Any token that is not in the vocabulary, we specify with a specific unknown token, because people might make mistakes to come up with new words, and your model should not break, right? You should have a fallback option. We usually call it a set of V, and basically this is the size of V, which is the size of the vocabulary, and each word of the V should be represented as a vector, because that's what our transformer model wants. We want to represent each word as a vector, because computer does not understand this. We should convert it to numerical way, right? So what is the now we should get into what are the nice ways of converting each word to a vector. That's what we want to discuss today now. So do you have any ideas before looking at the solution here? Maybe I should move here. So do you have any ideas? Like imagine you have a set of tokens, all tokens in English, and you want to have a mapping of each token to a vector. What is the solution that comes to your mind? And one solution is to just assign a random vector to each token, right? Just for a random.rand and do a random vector and just save the assignment somewhere. Do you have any other ideas on how can we find a mapping between tokens and vectors that we can use for transformer models? Like if you wanted to just make a mapping in a code, in an assignment, what would you have done? Any of you might have suggestions?
Sort them alphabetically, you have the space of all possible words.
Exactly. So that's one idea that was actually here. So one idea is that we just sort them, or maybe like even not sort them alphabetically, but sort them in some way. Like there should be a list. And then imagine I is the first token of the list. It means that it's a vector. That first element is 1, the rest are 0. We call it the one-hot encoding. Or imagine am is the second word of the vocabulary. The second index is 1, the rest is 0. Attend is the third word. So the third element is 1 and the rest are 0. This is one easy way, very easy way to convert word to vectors. And it's also nice because it has a lot of zeros, and in computation, it helps us. Always in linear algebra, when you have a matrix full of zeros and only some elements 1, it would help a lot in all of the multiplication, matrix multiplications, and anything that you want to do. So it is, from one side, very nice, right? You just convert each word, and it's very simple. Imagine you want to find what is the vector for a certain word. You just find the position of the vector in the vocabulary, and then the result would be a vector. Every position 0, that position 1, right? So this is the very simple way of converting words to are converting words to vectors. However, there is a issue here. Should I give you time to guess? Just maybe some seconds. I don't know. If you have seen this, it's very easy for you to say. But if you have not seen, I don't think it's easy at all to say. Do you think any issue there is with using one-hot vectors? Like this. I think
If
if
a
you have
vocabulary like big
Sorry?
enough, if a vocabulary is like super huge, you just like will get one and like lots of zeros,
That's
and you will
true.
just lose
Exactly.
the meaning of the word.
However, in practice, because it's just one per, I think it's also the answer to this question, maybe. ASCII, I'll come to it. In practice, if it is just one per row, you can save the matrix in a smaller form. You call it sparse matrices, right? Because there are a lot of zeros. And because the computation is faster, in practice is okay, right? What you said is true. The matrices are bigger. But because it's very easier to compute, we don't have a big problem regarding that. So it's a downside, but it's not a very big downside. But that's true. I don't know what this ASCII, what was the solution, because I think I missed the chat. But it was maybe the solution on how to convert. And that's actually true. You can also consider the ASCII codes. But the thing is, we want to convert one token. And the token, we are not converting characters, right? Because tokens have meaning. Characters don't have meanings. So yeah, that's something I just want to say. So let me say the downside myself, because as I told you, if you haven't seen this, you couldn't come with it. Wonder how the initial researchers came with it, actually. So there is a big downside here. Imagine two words, attend and participate. Or I don't know, two words that are synonyms, like or close, like and love. You agree with me that like and love are similar words, right? So a computer should consider also them as similar. However, you agree with me that like and, for example, parameter are very different words. So it would be nice if there was a way that the vectors of like and love would have been closer to each other than the vectors of like and parameter. Do you understand what I mean? Right? So we are converting words to vectors, and we want to convert them in a way that when we consider the similarity or the distance between vectors, the words that are closer to each other are actually closer when you convert the vectors. This would help us because with that, the model could learn from the similarities of the words, and it would help the accuracy of the model so much more. If we do one-hot encoding, we can't ensure this because each two vectors have the same difference. They are different in two positions. Like there is difference between I and am is the same difference between am and attend here, because they're like if you provide the distance or by any metric of the distance between the two vector, everything is the same. But we want to have a way that vectors that are for the words that are synonyms or are close to each other actually even be closer. So we want vectors to also have meaning. And that's what helped a lot in NLP when people tried to come up with vectors that have meaning themselves. Did you understand the problem? Any questions? You understood the motivation, right? What we want to do. We want to have vectors that have meanings. Or as in another way, we want vectors to contain semantic information. One-hot encoding does not provide it because, as I said, like a parameter, I love this example for some reason, we can't find the similarity between, like the distance between these two vectors is the same distance of these two vectors. Normal time series has semantic information because numbers, like imagine the stock prices of a company, can actually be huge, small. Like numbers, see, numbers have meanings. Sorry? It depends on you. You want the light? Or this is fine? Fine. See you. So normal time series has actually semantic information because in a time series data, numbers have meanings. If a number is bigger than the other, if the temperature is going to increase, the increasing has a meaning. So if we want to model text time series as well, we should also have some semantic information, some meaning up to the vectors. So all of you got the idea? There is no chat here. Perfect. So one possible solution is that we want to find a mapping. Let's just train a neural network for that. Let's just add a feed-forward network. that we input the vectors and we get the outputs. However, it's not enough because usually label training data is rare and it's not enough to capture the dependencies between words. What is the idea? Let's see what researchers have done to fix this problem. People said, do you agree with me that we have a lot of text in the world? You go to Wikipedia, you go to Google, search stuff, you have tons of text. They are not labeled, they are not data sets, but there are a lot of text that comes naturally in the world. Just imagine all of the books that have been written in the past 100 years. There are a lot of text. Imagine Wikipedia. We have billions of words for every topic that you might like. How can we use those texts to find embeddings? Is this possible? Because you have a lot of text and people were thinking, maybe we can use those long bodies of text to help us find vectors, find good vectors. And then we can just use the embeddings that we find from the whole Wikipedia to train a smaller transformer or a smaller data set. Because if we could find somehow good vectors by looking at the whole internet, we can use them to find really good mappings, and then those mappings could be used to any transformer model that we want. Did you get the idea? So do you have any idea on how, imagine you have access to the whole Wikipedia or the whole internet. Do you have any idea on how can we use it to find good mappings between words and vectors? This might be very difficult if you haven't seen this previously, but if not in 5 seconds, I will tell it myself.
Sorry, can you repeat?
Yeah, so the idea is that imagine you have the whole Wikipedia. You have access to literally everything available on the internet. How could you utilize it, use it to find good embeddings, to find good mappings of words to vectors? So if you haven't seen that previously, it's, I know it's not easy, so I will just say it. The idea is that in the real data, in the real text, words that come frequently with each other usually are similar words. Do you agree with me? Like imagine you are reading the whole Wikipedia. Do you agree with me that the words that come near each other, for example, if you read the whole Wikipedia, I would say the word Lausanne comes with the word Switzerland way more than it comes with the word United States. If you just count the occurrences in each sentence in the whole Wikipedia, right? So the co-occurrence, the fact that words occur with each other, come near each other, could be a sign of the similarity of the words. And then we can use them to somehow find good vectors. Did you find what I mean? It's clear for you? Like the idea is clear, right? We are using the text that is just available on the internet to find vectors. And that's actually a very nice idea. Again, we want to find patterns by looking at large bodies of text and words that come next to each other. If we look at the internet or Wikipedia, we find that Bern, Zurich, and Lausanne all come with the word Switzerland regularly. So they are 3 cities. This is what we can find. And what they call it is the first, one of the very early approaches of doing this is called continuous backup words. And to do that, we make a model to predict a word in a gap from the surrounding, from 5 words before and after, and this would be a sign of the co-occurrence. We are not going into the deep of how this model works, but you can consider, because it's not used anymore like in practice, we are using better models now. So it's just an early idea, but the idea is that we find the word to use from the surroundings. If 2 words occur with each other a lot in a vicinity of 5 words, it means that they are similar and thus their vectors should be also similar. So did you get the idea? Fine. Any questions online? Perfect. So here, as I said, in the approach of continuous backup words, we have a certain window size, and we train a model to predict a missing word in a window of 5 words. Imagine like this sentence. We pick 5 words, 1, 2, 3, 4, 5, and we want to predict the word de from the word when training model 2. Again, we want to predict 1 word from the surroundings. We are training the model to do that. And with the process of doing this, the model learns which words come with each other. Because if we want to predict the word de, it should know that de comes with these words a lot. So when we train the model to do this, it automatically finds the co-occurrence count And thus it can give us good embeddings. Did you understand it all? Fine. I know it's maybe a bit counterintuitive or a bit difficult, but this is the idea that we just use a very big data set and we just define a model to predict one word from the others. For example, imagine we pick this sentence randomly from the data. We mask this word. Now we say, okay, imagine we have a sentence that has 4 words. Predict the word each. What is the word here? The model should tell us this word. And the model will be trained to tell here that the word is missing. And by this process, the model learns to find which words come with which words. All fine? You understood the thing, right? We will see how it is applied in practice. We will see one example of a transformer model that is trained like this. So no worries. We will also say it again. But for now, let me show you quickly. Using here libraries, we are not doing any from scratch, right? Because no one does that. This is the continuous backup words model that I described to you. We want to find similarities of the words by using a corpus. So what we do here is that we just import the NLTK library, which is a useful library for NLP. We won't go over deep, but you can use it basically to download a data set. Brown here is a data set of a lot of text available on the internet. You can consider it like that. Brown is just a big set of text. Okay? You get the sentences of this data set. Brown.sentences. So if you run it, well, I should install Gensim. Sorry. I actually changed my laptop recently and I still don't have. Let's see if it can be installed quickly. Yeah, when I refresh my laptop, I still haven't installed everything. But yeah, so Gensim is just a library that you could use here, and now it should work. I hope the download doesn't take much time. So here, what this does is that it downloads the data set and gives us the sentences, right? Nothing specific here. Then here we train. I should also install NLTK. Sorry. Here, what it does here, that you might see here, we are training the model. We say, even if it is a one-time count of each word considered in the vocabulary, we want to output vectors of size 100, and we want to have a window of 5. Window, it means how many surrounding words we check. We should have a window, by the way. If you don't have a window, like maybe even Switzerland comes with Lausanne as much as it comes with the US, because there are a lot of articles in the world that also are talking about countries and they have United States somewhere and have Switzerland somewhere else. You should specify window size such that you only keep relevant words, right? If you, for example, Lausanne is, you may have seen a lot of examples that they say it is located in Lausanne, Switzerland. So it means Lausanne and Switzerland come a lot with each other. So you should specify the window size. Was it installed? Perfect. So let's do it here. Perfect. And you can print the data to see how it looks like. Basically just a set of sentences. So as you see, there is an array of arrays, list of list. Each list is the tokens of a sentence. And you may see that here the tokenization is not very perfect. As you can see, like here, they didn't, for example, split the apostrophe S. It's not the fanciest tokenization ever. It's just a toy example, right? So here you just train the model with, for example, 15 epochs. Let's just do it. I hope it doesn't take long. And then when the training is done, you can get the vectors of the model and then find the similarity between vectors to see if they make sense. Like it's the exact thing that I said, right? Instead of one-hot vectors, we now have vectors that have meanings. For example, what do you think would be the similarity of these two compared to these two? Any idea? It would be, of course, the top one will be higher, right? So let's see what is the example, because I have already run it previously, which is, you can see it's like 3 times more similar. And if you run it for more epochs, oh, I should not show it later. But okay, so for now you saw this, right? Because I don't want to spoil the next question. It's like 3 times more similar. However, I have a question for you. What do you think would be the similarity between light and hate compared to these two? Like, imagine like this was 0.15 and this was 0.05. What would you think would be the output of this line? Any ideas? You mean between those two? Why do you think it's more than like and parameter? They're opposites, right? Exactly. They come together in text, right? Like and hate, maybe there's a lot of stories that talk about like and hate. So they come together actually. And even the interesting thing is that the value is more than like and love, from what I remember. Yes. So it means that in the data set, somehow like and because many people don't like say like and love in the same sentence, but they may say like and hate in the same sentence. Interesting. So this is a good point that these scores do not mean that they have the same meaning. It just means that they are similar in semantics. They are connected, exactly as you said. Connected was a great word. So you should never use this to find synonyms because it would give very wrong results, as you saw. If we train for more epochs, actually the differences are even more pronounced. Like you see, this one, like and parameter is now even less. When you train it for more, it learns more than like and parameter have nothing in common. But the scores of the two others are increasing. And as you train with in more epochs, the scores make more sense. So everyone got the idea? Any questions on this? On the similarity vector. So imagine now I will later show you a model on how it works, how we can train such a model. But for now, imagine that we have such a model that gives us these vectors, and then we use these vectors to convert words to vectors. And basically, when we want to work with an NLP problem, we first convert the words to these vectors, and then we use them in transformers. All right? Fine, fine. Let's see if you have any questions here. No? Yes.
So essentially, we're training a neural network to acquire an embedding that has some sort of meaning that we want it to have, right? But why do we do this initial pre-processing step? I mean, couldn't you just make a part of the neural network that we're training?
Exactly. So that's how it's done in BERT. And we will see. Yeah. This was announced before Transformers era. So this is from a paper that was from I don't know when, but it was before Transformers. And at that time, seemingly the models did not have enough power to get the both at the same time, but Transformers can do it. So in Transformers, we have the embedding as a part of the whole process, as we will see.
So we don't
No, we don't do separately. But still, when we train the transformer, we still can use it to convert words to vectors. And that's actually useful. For example, imagine you are searching in a lot of documents and you find the closest document. You can use these vectors to find the meaning of closed words. So still we use it separately, but we don't train it separately. That's how it's done. And we will see like in practice, but yeah. So no one, I think, does this approach a lot these days. I mean, it's faster than transformers, like it's more efficient. As you saw, the training finished in mere second, but in transformers it will take more. So still there are some merits, but the state of the art is transformers. Yeah, perfect. Yes. So these are the cosine similarity between vectors. Like when you do the inner product and you basically divide by the size. So it's basically a function of how the vectors are different in the space. Like, from a linear algebra point of view. Yeah, exactly. It's a function of the cosine similarity, as we call it. This is just, I mean, you can use like different distance functions as well. This is just an example of how the two vectors are close to each other in that space. Because this is a multi-dimensional space, right? I don't know, 100-dimensional space. And we need to find a way to find the similarity between vectors in that space. And here they're just, I think, using cosine similarity, like just basically calculating the inner product and then dividing by the size of each vector to normalize it. I think the similarity should do this actually. Maybe we can method that is used for. I want the copilot to tell me. Yes, it is in this cosine similarity seemingly from what copilot now wrote. So yeah, basically you are using a function of the inner product of the two vectors to find the similarity. But you can use anything you want. Yeah. We know how to form the inputs to the models. Previously, models that had limited label data had also limited semantic information of the word similarities. But however, we now have embeddings trained on a vast corpus. There is one challenge before getting to, actually that addresses your question as well, but I wanted to wait until now. There is one challenge that you might think, okay, as you said, why don't we find the embeddings also in the same process? The thing is, usually for the data that we have for data sets, they're not very big. Like we have limited data sets. But we have lots of text on the internet, then we can use them to find embeddings from the data, right? So we had a lot of text, but the text is not useful for our final neural network for classification. Imagine we want to classify text as happy or sad. We have lots of text in the world, in Wikipedia, that we can use to find embeddings, but we don't have them classified, this is happy, this is sad. So we can't use them in the neural network to find the loss function, ideally. So that's why people pre-transformer era and pre-transfer learning era, they just did it separately. They first found the embeddings on the whole internet, then use those embeddings to train a model with the data that you have. However, people thought, why not also try to train the models on a vast amount of data, on the data that we have on the internet? You might think, but how that would work? Imagine we want to make a model that would classify sentences as happy or sad. Do we have a lot of data in internet about that? We should pay someone to say this is happy, this is sad, right? Imagine before GPT. Now GPT can do it. We'll see how. But imagine before GPT, you had to hire someone, like literally pay them money to label them. This is a happy sentence, this is a sad sentence, this is happy. And this, you can't do it with all the text in the internet. Right? So did you get the problem, right? So we still have problems here. People saw that training data on the whole internet is a good idea, but in practice it's not very useful because we don't have labeled data. However, you might remember the concept of transfer learning. Do you remember that from Friday session? I mean, some of you were not there, so I will do a recap. What was transfer learning? We saw that when we have two different domains, imagine we want to make a model that would translate from English to French and a model that would translate from English to German. So we have two data sets and we are training a different model for each of them. We have different predictions and that's how we do it, right? Another idea was that we train, first of all, a model with more data. Then we split the model into a body and a head. And we just change the head for any other task that we want and keep the body. So each time we want to train the model on a new data, we freeze the weight of the body. We don't do back propagation on the body. We just do back propagation on the head. Imagine in the example of translation, we train a model for translating English to French. Then we split from some part, from some layer to a head and body. We keep the body freezed, the weights freezed, and we just change the head on a data set from English to German. The idea is that maybe some of the concepts that are useful from translating English to French are also useful when we want to translate English to German. That's the whole idea. And actually, this is also very useful because it takes way shorter time to train. You only need to train the head, and it's very less computational expensive. Also, if you have a good model, you can use that body everywhere, and that would help you with have better predictions. So there are a lot of benefits, right? You can see there are lots of benefits in just keeping the body and changing the head. Also, the bigger a model is, the more data you need to train it well. So here, if you want to train again from the beginning, it would not be very valid, and it would be even maybe low accuracy. But if you just train the head, there are less weights to train, so the model would work well even if you have a smaller data set. So you got the idea of transfer learning, for which I mean, some of you were here, but for some of you were not here. Transfer learning is basically we just keep some weights and we change just some of the last layers. We just change the head, or as we say, we fine-tune it. So it's like pre-train and fine-tune. Fine-tune means basically changing the head only. So we just change the head a bit or change the weight a bit, change the weight of the head a bit so that the same model would work on a different task. Any questions? So we train a model on a vast amount of data, then for each specific task, train the head on that task. It allows much less training data to be effective. Also, we learned good embeddings in the process. Actually, OpenAI was a pioneer of this back in the day. However, let's see how it applies to our case. Do you agree with me that if we find some way to train the body on the whole internet, then we can train the head on just a small data set that we want and have good models? Do you agree with me? Like, this is the idea of transfer learning, right? We saw that training a model on the whole internet works, but it won't work for us because we didn't have the ground truth results and we couldn't do the loss function. But if we somehow could train the body first, or a body and head first, and then change the head for the specific task that we want, we might come up with very good models, and we'll also come up with good embeddings, because embeddings are the initial part of the body that's also trained with the body. And then we can reuse those embeddings for different tasks. So when we want to do different tasks, we just change the head. We don't change the body anymore. We keep the body. The body has information of embeddings and also some general information on the language. Like it gets some meaning from the language, and then we just change the small head for each task that we want. Imagine we train a very good model, and for translating from English to everything, we just then have a head for French, have a head for German, have a head for Italian, and so on. So that's the whole idea. Let's try to see how can we train a transformer body with, how can we train a transformer body that is actually useful. We can just put different heads on top of it, and then it would be useful in a lot of different tasks for us. That's what we are gonna do on the next half, to find how can we map transformers with transfer learning. And there are two different variations of the transformer architecture that we will discuss. I think now it's 5, so we can have a quick break. And then we'll come up to discuss two architectures. So see you in maybe 5:10. It's fine for you? In 8 minutes. In 5:10. If you have any questions, let me know. Was used with RNNs, right? So this is just a change of the RNN architecture to just fix the bottleneck problem. Then this was this weird paper. We haven't started yet, by the way. We are just considering questions. This was this weird, not weird paper. It was actually a very nice paper, but interesting paper called "Attention is All You Need." That they said, okay, we just can remove RNNs, and they interestingly showed that it works. No one would believe that this works, but they just removed the RNNs, just kept the attention. So it was actually a backward move, but surprisingly it worked. So it's one of the surprises, actually, in a sense. Yeah, actually. So in the end, transformers are better, in a sense. Like these are the state of the art. And now the whole GPT and everything is based on transformer architecture. So that was a highly influential thing, that RNNs were a solution to something that could have been solved a different way. But people just needed the RNN to come up with attention, and then the attention was used to just dispense RNNs at all. It's very interesting how it went, right? Especially when I was following the news over that time, and when the paper came out, everyone was saying, wow, RNNs are not any good anymore, and everyone was surprised. So yeah, it was a very influential paper, I have to say. But yeah. Okay, let's get in again. So 3, 2, 1. Perfect. We saw just before the gap that the idea of transfer learning can work if we can make a model that would work very well, we can train a very good body, and then we just use different heads for different tasks. So now we want to see how we can make a good initial model from the data that is available on the internet. So how can we make the initial body? For the head, it's simple, right? You just have the model, you give it the input data, and you do backpropagation. Very simple. So for head, it's just a simple training process that you already know. But to have a good body, we need to come up with ideas. How can we use the data that is just available on the internet to find insights? So let's see two approaches that people did with transformers. This is a general architecture of the transformer, as we already saw. We had the positional embedding. That was the way that we could circumvent the problem that RNNs had sequential info, but transformers didn't. We had the encoder layer that has some info on it. I won't go over the details today. You can see it in the transformer lecture. It's not needed today, like the normalization and a lot of stuff. So we had the encoder and the decoder part, right? This is just an example of encoder and decoder. There was two ideas that went very famous in the world of transformers, and both of them were very successful. The second one, way more successful, but I will cover both. The first one is called BERT, which means bidirectional encoder representation from transformers. And the idea is that we only consider the encoder here. So ignore the decoder part of the transformer. Imagine we only have the encoder and we just want to train it, right? So we are just here thinking, in BERT, the idea is just about thinking about the encoder of the transformer, and let's see what they did to come up with a very good body that can be useful for a lot of tasks. Let's see. It was introduced by Google researchers, actually, in 2018. It was a big model at the time, like 110 million parameters. I mean, this is nothing compared to today's models. Like GPT, even GPT-3 had in terms of billion parameters, right? So this, at that time, it was pretty big. And there was also equivalent BERT large, which was 300 million parameters. But BERT base is actually a model that you can run on your laptops easily. Most of our laptops could even run it nowadays. So what is this? Again, saying BERT is basically a way of training encoders of a transformer that can be used to later do transfer learning. So let's see what they did in the paper. Again, I'm saying this is an idea, right? This is an idea on how you can train a body. We are seeing two ideas here that were successful. One of them is the idea of BERT. Let's see what they imagine. This is the sentence. My dog is cute. He likes playing. You convert the sentence into token embeddings. And this is done by a network, by a kind of a neural network that is trained with the whole process of BERT itself. Because we are training on a big data in the internet, it also can be used to come up with the embeddings. So this is the input sentence. We have some interesting tokens here that are added in addition to the sentence. So here you see, my dog is cute. He likes playing. First of all, playing is converted to play plus ing. But for some reason, likes is not converted. I think because it's not two example. I think in practice, or like would be also like plus s. It's just a two example, right? And here we have a specific token here. Maybe it's a bit small for you to see from far, but here, let me zoom. Here we have a token called CLS. We will see what it works, what it does, but it's always in the beginning of the text. Then we have a sep token that separates two sentences. So just consider these two specific tokens. We just add them to the sentences. This is one of the ideas in BERT. And then we convert each of them to token embedding. These also, CLS and SEP also have their own vector equivalents. Then we add position embeddings also, as we already know. We also have segment embeddings. Segment embeddings specifies the words that are in the same sentence. You see, my dog is cute. All of them are added with E of A. He likes playing is added to E of B. So this is a unique value per sentence. It helps the model to find when a sentence is finished and another sentence is started. Because the authors of this paper thought that this is useful to know if we want to do anything regarding text. Because the sentences also are units of meaning, right? So when we do token embeddings, we are converting each word, but we are not considering the effect of sentences. And by adding segment embeddings, we are also considering the effect of each sentence. Because when the sentence finishes, another starts, there is something going on. It means that the topic is changing a bit. So, all fine? Did you understand what I said? Perfect. All fine. No chat yet. So this is the first thing that they did. They add the token embedding, segment embedding, and position embedding. Why I'm saying this, you may see I just use the code. If you read a lot of papers that have done BERT, they will say that. For segment embeddings, we use blah, blah. For token, so it's always useful to know this. Not that you are going to code it from scratch yourself, but it's always useful to have an idea. Then, this is the input, right? What did they do with the input? Like, what is the task that they are? So for each model, if you want to train it, we should have a task, right? For a classification model, we have the task. It's either sad or happy, and we just do the backpropagation on the loss. But when you want to train something on the whole internet, we should come up with our own task. We should define a task from the data such that no human is needed to label the data, because that would not be useful, right? If we had a human to label all the data on the internet, we didn't need BERT, or we didn't need any other model, right? Like this. We didn't need transfer learning. We have to somehow, given the data from the internet, come up with a task ourselves. And that's actually what I also discussed in the beginning of the lecture. We call it the masked language modeling. We hide one word and we ask the model to predict that word, right? So here, I am mask the winter bootcamp. What is the most probable word that comes with mask? The model should say it is attending. And how the model does it? So BERT model is sequence to sequence, right? As I showed the diagram of sequence to sequence model, this is also a sequence to sequence model. We don't consider the output here. The loss will be defined on the difference between the word corresponding to this position and the correct word. That's the loss that we will minimize. Did you get the idea? Yes. So I'm repeating. So first you saw the idea of masking, right? We are masking word and we want to predict it. How we do it in practice, BERT is sequence to sequence. Is a sequence like all of the models that you are seeing today are sequence to sequence models. So when we give it the sequence, I am mask the winter bootcamp, it would give a lot of output in here, right? We don't care about the output of these words in training. We just care about the output of this word, which should be attending. If it is not, we have a loss. And we backpropagate on that loss. So we just check these words. And basically, we are training the model to be able to identify the masked words, which is actually very nice because you can then use the BERT to find the missing words in a sentence. Or actually, that was one of the earlier use cases of BERT. You can use it in practice to predict missing words in a sentence or like that. So I am mask, and then it predicts the mask with the aim of the model to have word level information. And so did you understand this now? How the masking is done. So quick question. Do you think this would lead us also to find good embeddings? And if yes, why? Or if no, why? Do you think it would be helpful for embeddings? Like, would this also give us good embeddings? Exactly. Yeah. It's the same idea, right? So exact same idea. So it's paying attention to the surrounding words. And because we have attention weights, it can even pay more attention to the words that are closer. So it also gives us good embeddings. So not only it would give us a model that would predict the word well, but also gives us good embeddings that we can use for a lot of tasks. So it's very good for transfer learning.
So BERT is just word to vec with a larger context window and attention?
Sorry?
BERT is just word to vec with a larger context window and attention?
Well, yeah. So BERT is the transformer equivalent of that idea. BERT also has another component that I will tell you. But this component of the masked language modeling is basically the same idea, just applied with transformer architecture. The idea is the same, yeah. However, there is one challenge here that we didn't have in backup word. Backup word, we had a fixed window size. But here, we have a full sequence, right? It's a sequence-to-sequence model. Some sequences can be longer, some can be shorter. The way that they fix it is to add a certain padding token. That if the sentence is shorter than others, we just add padding to the end or to the start. Just something to know, right? Because if you don't do this in Torch, it will tell you the dimensions don't match and these kind of weird things. So you should add the padding to fix everything. So this is masked language modeling. We call it masked language model. There's also another thing that BERT does. So BERT is not only word to vec that we saw, it's also, we train also the model with another task. Predicting text continuation. We ask the model to predict if two sentences are continuation of each other or not. Let's see here. I am masked the winter bootcamp. SEP means next sentence. I learned a lot. Do you think these two sentences are related? Yes, right? These two sentences are related. Here, I am masked the winter bootcamp. SEP, Steve Jobs was CEO of Apple. Are these two sentences related? If we train the model, and here you remember CLS, right? Here we train the model to say 1 or 0, yes or no to the output of the CLS token. This would help the model learn sentence level information. So this task helps the model learn word level or token level information. This would help the model learn sentence level information. And that's also useful in transfer learning. I mean, you may think why it's useful, but in practice, it turned out to be useful. So these are the two tasks. Again, masking to find words, and then checking if two sentences come after each other. And by checking that, you just check the output of the CLS token. You just check it to see, yeah, that's it. Any questions? Did you understand the two tasks? Yes.
I don't understand the second one. Is it so okay, could you just
Yeah. So you mean what is the task of second one? So the task of second one is to see the two sentences that come after each other are continuation of each other or not. Do they is the second one naturally coming after the second one or not? Here, I am attending the winter bootcamp. I learned a lot. The second one is a valid sentence that comes after the first one. But here, I am attending winter bootcamp. Steve Jobs was CEO of Apple. These are not related. Yes. So how you do it? You have the whole internet, right? You just pick two sentences that are next to each other and pick two sentences that are not next to each other randomly from two different Wikipedia pages, for example. And then you have a lot of training data. So the idea is that for making this, you don't need a human. You can run an algorithm that will extract a lot of these pairs of sentences from Wikipedia. I don't know, maybe millions, billions of pairs. You just pick every 2 sentences in Wikipedia. There would be, of course, billions of them, right? And just make a lot of training data. Also here, you don't need a human. You just need to pick random sentence, hide one random word, and you have a training data. That's the idea. So we can train the BERT on the whole internet without human labeling. And we just have the human labeling for what we need the head. When we want to fine tune the head, which we need, which is a smaller data is fine. We just need a human to label the data. Right. So that's the idea behind BERT. All correct? Okay. So imagine now we have the BERT model and we have a big body. For now, what the body can do for us is just, first of all, filling the masks, and second, checking if the output of the sales token, if the citizens are after each other or not. So body by itself does not do much for us. But we can fine tune this model. We can keep the body, but change the head for a lot of different tasks. Imagine we want to check classification. If a sentence is happy or sad. I enjoyed attending summer bootcamp. This is happy. I hated following. I should change it to winter actually. I hated following the bootcamp. This is sad, right? With BERT, you just need to prepare a data set in which you give the sentences and then the output of the CLF token as 1 or 0. And then fine-tune the model, keep the body free, and fine-tune the head to just predict this. And interestingly, it works very well. It might be a bit weird, like why? It works very well, but it somehow leverages what it has learned in the body from the whole internet. It leverages connection between words, meaning between sentences, and somehow it can find that this sentence is positive and this sentence is negative if you give it enough sentences, which might be a miracle, but it works. So did you get the idea? You just, when you want to fine-tune the head, you just do it, ignoring how BERT was fine-tuned, how BERT was trained. You just keep the head free and you just give the input data. Sentence 1, 0, like binary classification that we had in neural networks. You just do it, and for some weird reason, it works very good. And that's very surprising also to the authors. And as a result, there were a lot of different variations of BERT going over time, and people were super obsessed with it. Any questions? I don't see anything. I think one of you have a microphone on because I hear something, a keyboard sound, but yeah, I think it's fine because there's no question. So as I said, you just have the base model and then you fine tune it, which means training the head. Let's see in the code together how this fine tuning can be done. And again, apologize, maybe this session will be a bit longer because I also want to show you another version that is very used these days, GPT, which is also a similar idea. But first, this is a easy way to see how you can fine tune a BERT. Here you just install Torch. I mean, you already have it installed, I think. You can install a set of libraries that would help you. There is a library called Transformers, which is very nice when you want to work with transformers. So this is a nice library that you can use a lot. This code also uses it. Let's see. This one is just for, let me also say this one. Hugging Face is a place that you can put your models. It's like GitHub or a social network for models. So you can put your models here if you want. You can train your models and push them here. It's not central to our code, but you can log into this hub and then push the models that you make to others so that they can download it. Okay, so what do you do here? You first load the data set. Here we are using a built-in data set. It's a data set of a banking intent, like this sentence means what, and like a set of things about the banking context. Like, for example, here, why am I getting declines when trying to make a purchase online? And then there is a label, like which department, for example, this sentence should go to, like something like this. Like which is the type of the banking request. So this is a simple data set. However, this data set is small. So we want to use transfer learning to use BERT that was trained on the whole internet, on a big side of an internet, to just fine-tune it on this small data set. So what do we do? The model ID is BERT based on case. On case is the version of BERT that they remove the capital letters. So everything is on like What's the opposite of capital letter? Small letters? I don't know, like not big A, but a small a. So they just converted it because the data here is also, I mean, data is capital. So I don't know why they use uncase. I don't know, like, but there are two versions, case and uncase. You load the tokenizer with this function, auto tokenizer that's from pre-trained. This just loads the tokenizer. And you define the function that would tokenize and add the padding because we need the padding. What does this do? It means that convert everything, basically add padding such that it reaches the max length of the data. We need it, as I said, because otherwise we would have problems. And then we basically run the tokenizer on the data set. So this is the map function in Python. I won't go over deep of the code. I can send you this repository later, but you just map, you use the tokenizer to change each element of the data set into the token. Then here, we first get the mapping of labels to IDs. We have to convert label to IDs because the model does not work with labels, it works with IDs. Then we load the model. This is a function that you can use from the transformers library to load the transformer model, auto model for sequence classification, because it's a model for sequence classification, dot from pre-trained. Here you give the model ID, it would search in the Hugging Face library for that model, and BERT is already there. So it would load the BERT model for us. You give how many labels do you want, and the mapping of the labels to IDs. Here they define the function for evaluation. It's just nothing, a function for just evaluating computing metrics on the data. And here is the important thing. So we have a training arguments class, again, in the transformers library that can help you a lot. We say a lot of stuff here, all the parameters. What is the batch size, the number of epochs, learning rate, what is the name of the optimizer you want to use, how many steps do you want to go, and then log, and a lot of different things. And you just then run the trainer on the model with these args. You give the training and the evaluation data set and the metrics to compute. Here, what it does, it will actually fine-tune the BERT with your data. You just call trainer.train, and then you can run it. You can, for example, then run it with the pipeline function. You just give the model and the tokenizer and give a sentence. I have been waiting longer than expected. And then in the output, it will tell you it is this label with this score. And it actually works pretty well. I don't know if they also evaluated the scores, maybe somewhere. Yeah, here. Like you can see, this is train runtime. Like they didn't compute for test for some reason. But you can see the F1 for training is actually pretty high, at least. It means the model is learning something, right? We saw that the model was able to find the class of a certain sentence, although the sentence is very small. The fine-tuning process used the knowledge that was embedded in the BERT model from the every data that it saw on the internet to be able to also use in our downstream specific task. Any questions? I'll give you the code. I mean, in practice, I will also, every time I want to fine-tune a BERT, I will just copy the code, right? You don't write it from the scratch every time. You don't need to remember it. Just need to know the concept. A downside of the BERT, so in the remaining time, we will see a downside of the BERT, and then we'll go to GPT. One downside of BERT is that it needs a lot of memory and inference time because it's a complex model, right? So transformer models are generally complex, right? BERT is also complex. There are ways to reduce memory and time usage of BERT that has been applied in practice. One idea is quantization. What is that? You agree with me that all of these vectors are float values, right? And they are mostly in the Python, if you use a float, I think normally it's like 32 bits per float. What if you show numbers with less precision? Like show them in like 16 bits instead of 32 bits. Like you show numbers in less precision. We have information loss, and we then have performance, yes. But we have also benefits of less memory and less time to compute because the numbers are easy to multiply, and there's also less memory, literally half the memory size, right? So quantization is an approach to reduce memory and time. You may have heard like people who are running LLMs like DeepSeek locally on their laptops. Most of them are usually doing quantization. So they show numbers with less precision so that it gets less memory and less time with a small hit in performance. Usually quantization is worth it. While the accuracy would be lower, of course it will be lower because there's less precision. It's not that lower. The benefits are more. Questions? I won't go to the details. This is just for getting to know, like quantization could be a lecture on itself or also the rest. There's also another approach that people have used in their work that's called distant BERT. which is called knowledge distillation. I won't again go into details, but the idea is that you have a bigger model, you have the full BERT, and you train a smaller model, not on the original data, but just to replicate how a bigger model behaves. So you're somehow moving the bigger model to a smaller model. And interestingly, it works. So if you have if you make the BERT smaller, like with less number of parameters, and you train it again on the same big data, it won't work as well. But if you instead train it somehow with respect to the bigger model, that it tries to imitate and replicate and repeat what the bigger BERT does, actually it works quite well. We have performance loss, yes. We have hit in performance, but it's not very big. And again, sometimes it's better because it's way smaller and more efficient and less memory and everything. So for example, you can do things like this. I won't go into details, but imagine you have the true distribution here. You have the teacher in neural network. We call it teacher and the student. Teacher is the big network. And then for each sentence, like here, India was the first country to grow. And then there's the math word that we want to predict here. The teacher said mango. And it gives us a distribution of the words. And we use this distribution and we make the student network trained such that it gives the same distribution as the teacher for a set of sentences. Did you get the idea?
Excuse me?
Yes.
Is it possible to distill knowledge from one model, big model, to another smaller model, but like with different architectures? Like for instance, I don't know, like using BERT to distill small GPT, they have like different tokenizers, inputs, and different outputs. Like, is it possible?
Yes, you can. The short answer is you can, but
And
not
is it effective?
comparing
Like,
distributions.
so it's not that effective, right?
It is actually. So let me tell you. So here in this example, we are directly comparing distributions, right? Distributions are very unique to the model. However, you can just use the output. For example, what people have done actually in the literature is to prompt GPT for the correct answers and then use them to generate a lot of data for training the BERT. That's also a kind of distillation, but it's different in nature. And that can actually work or not work depending on the task. Yeah. So you can do it in practice. But usually they say distillation loss and this kind of metrics, it means the same model, but the same idea can be applied to different models. If that's answered your question. So in practice,
yeah.
yes, there are papers. I can even send them in Discord. Like there are papers that distill from 2 different types of models. I will send them in Discord later.
Thank you.
Perfect. So did you understand the distillation, all of you? Fine? Like the idea is this model should replicate or imitate the distribution of the bigger model. Here, this example is the same. Yeah, we are actually this BERT, the example of this BERT, which introduced this in practice for the first time, is just a BERT, but with less number of parameters. Like I don't remember exactly how much, but it was like half or something. I don't remember. It was less number of parameters. You can also do different types of distillation. You can use cosine similarity between the embeddings. You can use a lot of different functions. I won't go into the details, but somehow we want the student to behave like the teacher. That's the original idea of distillation. And I will send you some extra papers and resources if you want. So we saw one downside of BERT. Any question until now? Before we get to the next part? Perfect. So, from what you saw, there is also another downside of BERT. I mean, if I ask you, can you give me another downside? Maybe it's not obvious to say when you haven't seen. But another downside is that it can't generate text. Why? First of all, we want to generate text a lot, right? When you're asking GPT to give you an answer, when you make a chatbot that wants to talk to you, you are generating text, right? So we want models, also good models, to be able to generate text, like ChatGPT. However, this model, you agree that the mask depends on the things before and after. And thus it can't continue the text because it hasn't seen what's coming in the future. So if you use it, you can maybe use it. You say, okay, I just masked this word, and you can generate another word, and so on and so on. Like, for example, imagine you want to generate, I am attending the winter bootcamp. You just write, I am mask. And ideally, this would tell you attending. And then you again add mask, and it should tell you there. And you again add mask. And then you should add winter, right? You may think this would be useful, right? You may think this would lead to BERT generating text. However, here, do you have any idea what can be here inside mask? If you're a human, like how the model should know? that you should write attending. So it's not very obvious, right? In practice, BERT is not applicable for generated text, and if you use it, you will receive very weird text. You will receive it won't work. Maybe we can try. Paris is the capital of France. You would expect that he would answer, right? Let's see. I hope it should answer. This is BERT actually. So yes, you can see the distribution of output. Capital, and the rest are very small, so it doesn't mean anything. Basically, the answer is capital, like the probability is 0.982, right? But here it also works because it's very obvious. However, you can see it's not as strong. We have the probabilities that are pretty smaller, and we have also a lot of big probabilities that don't make sense, which means that it has gone very useful. Maybe if we like the answer to the live is, you see, it doesn't continue with words. It loves to put usually punctuation marks, unless the word is very common. Like Paris is the capital of something is very common. But here, it doesn't continue the text well for us. Like we can't use it to continue text. Even if we put the colon, again, it's not, you see, it can't continue text well because it's not trained in this approach. It's trained to look at both directions. Be in the BERT means bidirectional in a sense, right? So it looks in the both directions in a sense. And I mean, it's not the exact same thing, but yeah. And it can't continue text for us. So it's not useful if you want to make a chatbot with it that would generate text for you, would write text for you. It's just useful for really feeling the mask or for classification. Any questions on the example we saw? Fine. So first, before getting in, text generation is very useful in a lot of different things. Summarization, you give a full text to a model and ask it to summarize it. Translation is the example of text generation, right? Because you are converting one to another and you want to generate text. Chatbots like ChatGPT are generating text. So what is the general idea that we need for text generation? This is I think this part of the lecture is the one that you connect the most with because you have all your ChatGPT, I assume. The idea is we want to predict the next token based on prior tokens. Do you agree with me? Like this is very obvious, right? This is the task of generation. We want to predict next token based on prior tokens. You can consider it as a kind of multi-class classification. How? Imagine you want to predict the most probable token that comes next. You agree with me that if you consider a classification problem, that you are classifying what is the next token from all the tokens in the vocabulary. It's like a very big classification problem in which for every token in the vocabulary, you say, what is the probability of this token to occur? Do you agree with me? That this is, in a sense, a very big classification task. But we don't have like 10 classes. We have millions of classes, like the number of tokens. So we just need to predict what is the most probable token that will come next. Fine? How is it done in practice? Imagine we want to generate this text. Natural language processing is an exciting field for several reasons. And then it wants to generate continuation. First of all, we generate one token. And that token would turn out to be human here, right? Then we again get the full text until human, and then ask the model to generate the next token, which would be computer. Again, we give the whole text until computer to the model and generate it and ask it to generate the next token, would be interaction. So we generate one token at a time. We call it autoregressive approach. This is called autoregressive. So you start from the beginning, you generate one token, you add that one token to the input, you generate the next token, you add both to the input, you generate the next, and so on, so on. So each step you are generating one token. This is why in ChatGPT you see the words are typed one by one, because it's generating one token at a time. Did you understand this, right? It's fine? What is autoregressive, right? So in GPT, which is the abbreviation of generative pre-trained transformer, we are just dealing with the decoder part of the transformer. And what we do is The model that exactly trained on the same word. For GPT, it's very simple. It should be able to predict the next word that would come in the page. So there's some noise from here. Someone has the microphone open, maybe if you could close it.
You were just checking with Adrian, time steps, right? So
I can just reduce the
I think he has a setup
Really?
where he could
participants.
do a customized
I think, yeah. Could I?
practice test.
No, I can't. The chat and pin. I'll just reduce the volume. Okay. So, for GPT, it's actually simpler than BERT on how you train it. Imagine you get, again, a Wikipedia page or a page on the internet. You just start from the beginning. Imagine this is a Wikipedia page, right? You just start from the beginning. You start with this. Give the model pre-trained, it should tell you on as the output. Then give the model pre-trained on, it should predict A. If the model pre-trained on A, it should predict lot. You see, from even a single page, you can make lots of training data and just use them to train the model. You get it, right? It's very simple, right? This one is simpler than BERT. You just use the model to continue doing it. So again, we want to have a model that would be able to generate text, and that's what we're using, right? So we pre-trained GPT on they pre-trained GPT-1. They pre-trained on 7,000 books, which is 13 gigabytes. This is nothing compared to what GPT is trained on now. Like, this is nothing. But at that time, they trained on 13 gigabytes of 7,000 books, and they did chunks of 512 tokens at a time, trying to predict the next one. Then at inference, they give an input. When they want to run the model in practice, they give a partial text, and they generate words one by one. Right? So, any questions on how GPT is trained? I think it's fine, right? There's one catch here. When you train a model on the whole internet or on a part of internet, each time you want to predict one word, imagine like this is the web page of Wikipedia. This is the input you give to the model. What is the output that the model should give? Text, right? Because the next one, right? However, when you're using GPT in practice, each time this text is not from the internet. It's generated by the GPT itself. So any error that it makes propagates and increases over time. If you get what I mean, right? So imagine instead of on, it used a totally different word. It would not only ruin that prediction, but the whole prediction. So that's the very difficult thing about GPT, that the way that it's trained is different from the way that it is run in practice. In training, we just give the real input, but in practice, each time you are generating a word, you are using the previous output from GPT itself. That's the main difference, and that's the reason that even if we make a very good model on everything on the world, it still might not be able to work someplace. So just saying as a catch. Did you understand that? Fine. Perfect. We learned about GPT, right? Then the progress continued. GPT-2 was trained on more data in the web. It's increased from 13 gigabytes to 40 gigabytes. And they provided in 4 different sizes, from 170 million to 1.5 billion, which was a lot at the time. Like this number of parameters that the model has. Again, nothing compared to a lot of models we have now, but it works. So let's see, this is an example of GPT. This is the example that I took myself. Again, it's summer. I liked attending the summer bootcamp, and then I asked it to generate. It said, but I didn't want to go to the summer camp. I wanted to go to the summer camp because I wanted to learn how to do it. I want to learn how to do it. The text is fine from a syntax point of view, but it's not very good. Like if you give this text to someone, they might think you have gone mad or someone, right? Are you drunk or something? Like this is not a good sentence in a sense, right? This is just a common thing that people say. Well, our model has gone mad, or our model has gone drunk. If you heard this, like the model is somehow giving information that does not make sense. But it means that when it generates but here, it's very nice because it has learned that usually after I like something, it comes but. it somehow is learning something from the underlying data, which is very nice. So did you, any questions here? I mean, it's just an example, right? But this is how GPT-2 did. Then OpenAI went to GPT-3, which had 175 billion parameters, which was really a record at the time. And you can see how the text is way better. It turned out to be more than just an addition to my knowledge, but also it leveled up my C# skills. I don't know why they introduced C#, but it was challenging and enjoyable to attend a fairly difficult class. You see, the example is now way better. And it means with more data, with bigger size of the model, the accuracy improves. Like this is what we also expected, right? Usually with bigger models, you have higher accuracies. But you may have heard that sometimes bigger models turn into just, sometimes when you make a model just big, it would actually decrease the accuracy. But actually, in the case of GPT, it turned out to be more useful for generating text and for continuing text. Even better is GPT-4, of course, if you all use these days, like the one that you use in ChatGPT. Because it offered me an amazing opportunity, it's like broaden my horizons and a lot of things like this. You see here, some stuff are weird still in GPT-3. But in GPT-4, it was solved way better. And as the size of the model increased and they used more data and better metrics, we saw the model is improving constantly. However, we don't use only GPT for generating, right? For continuing text. How many times have you used GPT to continue a text? 0 times? 1 time? I don't think there are more. You ask questions, right? You ask questions, it would answer. It can do a lot of weird things that were not possible 2 years ago. It could solve a lot of questions on our exams. Like this was this paper recently done in collaboration in EPFL that actually GPT is able to solve exams of a lot of questions on, for example, bachelor grade at EPFL. So GPT can do a lot of more things. So how did they come to happen? Now we want to explore this. So they trained GPT to do continuation. However, it's also very successful in doing other things, which you will see now. First of all, before getting to what GPT can do, apart from continuation, let's explore a bit more how this continuation is exactly done. Because if you just pick the most like token at each step, do you agree with me that every 2 questions you ask GPT would lead to the same answer? If you just pick the most probable token, do you agree with me? Right? If you just pick the most probable thing that would come, it's just 1 token at a time. So every time you ask a question, it would say the same thing. However, you know that GPT does not do that. It adds a variety to the question as well. So how it is done in practice? First of all, GPT finds the probability of each token in the vocabulary. What's the probability for them to come next? And for that, they use the softmax, again, as the probability function. For example, here, the weather in summer is, imagine we run this to GPT and the outputs are hot with the probability of 0.6, warm with the probability of 0.3, and cold with the probability of 0.5. There are different things that we can do here. First, we can just pick the first one, hot. Always. We will just pick the first one, which we said is not always useful. So it's also better to have variety in the text. And it also makes the text usually repetitive, because usually the words that are very common have higher probabilities. So it makes the output text very unnatural and repetitive. So we want to also pick from the ones in the bottom as well. However, what is the threshold that we should pick? Should you also pick cold? Because it would make it wrong, right? The weather in summer is cold. Doesn't make sense. So what is the threshold? What is the line that we draw? This is a question that people who design GPT should have answered. Did you understand the problem until now, right? You don't get what's the issue. So what did they do? Is applying a couple of ideas to correct mistakes over time and to be able to pick tokens that are most probable. Let's see what they do. First of all, the idea that is very common here is beam search. At each step, instead of 1 token, you decode B tokens based on their probabilities. It can be from, for example, the top K elements of the list. Like you can say, I pick 5 tokens from the top 10. Or you can use it based on probability. Like I can pick 10 tokens from values more than 0.3. You can do both. We call them top K or top P strategies. Top K means you pick from the top K elements of the list. Top P means you pick from the probabilities more than a certain range. You can use both, like whatever you think is better. Right? All right? So then at each time, we select B items based on the probabilities from the top K or top P, and we continue until a certain end, and we calculate the probabilities of the sentences to see which one should be. For example, here, we want to generate the sentence, the green which arrived. We try to start from the beginning. We either generate this with the probability of this, and we generate arrived with another probability. Then for the next word, after arrived, we generate the and which, and then we generate green and which. So now we have 4 sentences. Arrived the, arrived which, the green, the which. Did you understand that? Like maybe I can zoom. Like now we have 4 different candidates. We calculate the probabilities of these 4 sentences to happen. How can you do it? You just multiply the probabilities, right? The probability of arrived times the probability of which given arrived. Like it's just a probability. And we pick these 2 because these 2 have higher probabilities. Like the sentence arrived there is not very probable to occur. But the green and the which are probable. So we keep these 2 and we continue. So this is the idea of beam search. At each time, we pick the high probability ones among a set of top K and type P and continue. Any questions? I would go into the math details on how it is done, but this is the general idea on how you pick the possible answer, and that's why each time you prompt GPT, the answer might be different.
So we kind of calculate top
Somebody's
K.
talking?
Yeah. Hi. So we
Yes.
just like kind of calculate top P answers, like top P combinations, and then just like multiply it, right? Like, and they get the highest probability sentence. If I
Exactly.
understood
So you
correctly.
multiply them, but I mean, actually, instead of multiplying, you sum the logarithm. Yeah. Because when you multiply, usually they get so small. So in practice, it's applied by getting the logarithm and then summing them together. But yeah, it is indeed, it means multiplying. Yes. So as you can see here, the probability of a sentence, the probability of the green which arrived is actually the probability of the plus green given the plus which given the green plus arrived given the green which and so on. Like this is just a conditional probability that we know from probabilities course, right? So, highest probability sentences, because those are the sentences that are most likely to be true. Yes, then you pick the highest probability. For example, you keep always the 2 ones, and then whenever you reach the end, you just stop with it. That's a way of doing beam search. You can continue until a certain limit, or if all of them reach end, and then just pick the highest probability. This is one idea. All right.
The question is just what pressure differential you apply now.
That's very true. So here we have one catch. We are evaluating at each step. Like here, you are pruning these 2 branches. So we do this evaluation not in the end, because in the end, if we do it, that's actually true. Actually, yeah, they might be wrong. Yeah, so to remove the effect of length, we do it at each step. If we went to the end, the different sentences have different lengths, and that might not be valid. Yes, you're right. So there are a lot of things that, like the code, have a lot of if else and all of these things to make sure it actually works. This is just a general idea. Yeah. This here we have a K of 2 and perfect. So we are almost here then, so it's fine. About the temperature. So there's also another thing called the temperature. What's that about? You remember the softmax if you were attending the lecture. Otherwise, softmax was just a function to convert a set of values into probabilities. Like for example, we have a set of values and we want to convert all of them to be between 0 and 1. And the way that we did it, we get exponential and divided by the sum, right? So this is just a function that will convert values to probabilities. An idea that they did is that instead of just giving the value here in the exponent, they divided by tau, which is called the temperature. The temperature is a parameter of model that we can change. And the more that we increase it, what would happen here? If we increase the tau here, what would this fraction go to? Any ideas? Imagine if we increase it to infinity, like a big number. What would happen? So we like the value goes to 0, right? Sorry, the value of the exponent goes to 0. So e to the 0 is 1. So it will be 1 over 1 plus 1 plus 1 plus 1. So it's an uniform distribution. So it means that basically every word has the same probability to occur. But the lower you make the temperature, the distribution converts to just one word. So the lower the temperature, the more the temperature is, usually the diversity of the answer is higher. So if you want to make the answer more diverse and to make it generate more stuff, like as sometimes they say, make the LLM more creative, make GPT more creative, you can increase the temperature. And temperature of 0 is basically somehow deterministic. Like it's always the same thing, but the more you increase the temperature, there's a higher chance of choosing random other words instead of the most probable word. Because the probabilities are all equal. Basically, in the temperature of infinity, all of the words have the same probability to occur. And that's not a good model. Because a good model should have a set of probabilities that make sense, right? The more you increase the temperature, these become more uniform. And the more you decrease the temperature, these ones become more distant from each other. Do you understand that?
But more uniform also means the model is performing worse.
Performing worse, actually. Uniform is not good. But also maybe too strict is not good because we want to have some diversity. So we change the temperature usually. We will see it actually, so how it is applied in practice. So let me increase the size of it. So I have a prompt here. Yeah, so let's maybe say something like, give me a question, like anything you want. I just want to ask something from GPT. What is the meaning of embedding in transformers? Like this is the question that you want to ask from GPT, right? Here you have a temperature parameter. You see? So temperature of 1 or anything like 0. 0 is the lowest temperature that you can have. And you can see the output. When I run with temperature of 0, it's just very definite answer, right? So it works here. Temperature of 0 works. However, if we increase the temperature, like, I don't know, to 1.97, what do you expect to happen from what you said? Imagine 1.97 is very big. What do you expect to happen now if I run the same question again? So here the answer is correct, right? The answer is something very valid.
It will be really diverse.
What do you think would happen if I increase the temperature to a large number?
It will be really diverse.
So it is not infinity, but because the items are pretty small, it is indeed very large. So you can consider 1.97 to be pretty large. So it is you are saying it's close to infinity, right? It's close to uniform, right? So you would expect words to appear in the output that do not make sense. Let's see. See what's happening here. So the first ones are actually pretty fine because the probabilities are that big that even when you are uniforming them a bit, the temperature is not that big compared to probabilities. So it's still the first one, but as we go forward, the uncertainty increases, and you can see it generates random stuff here, like what the hell are these? Intellectual, like, sorry, these are random words that do not have any meaning, right? Because here the probabilities are such small that the temperature is considered infinity relative to them. And thus the distribution is also almost uniform, is a set of uniform, and basically you generate random responses. So you know you saw the effect of temperature. Any questions? All right. So let's get back the temperature to like 1. I think 1 is actually the default. Well, I can't reduce it. Let's refresh. Okay, 1, perfect. Now I want to play with some other stuff here of ChatGPT. We have a max tokens. This tells the model how many tokens should it generate. Like, let me ask this question. Say hello 100 times. Just hello. It works, right? I can stop it. However, if I limit the max tokens to like only 10 tokens, what do you think would happen? So there are two answers. Either it says that or it says I can't. What do you think would happen? Let's see. And then we'll discuss. No, it didn't. But why? The model does not have any idea of the maximum tokens, right? The model just is generating the next probable token. So it starts generating, but when it reaches the max token, the code breaks, the while loop breaks. So the model does not have any idea that it's so that's why usually it's not very useful to tell GPT, please tell me something shorter or longer. It can't really do it because something done outside of the model. Just wanted to let you know. It's just very quick observation. So it breaks after a while. But if we increase the max token to 30, it should stay a bit more. You can see that it generates 20, and then it says maximum token limit reached, response terminated. So let's again increase the token size. Now I want to play with something else. Top P, you already know the meaning. This stop sequence, you can say whenever it reaches that token, it should stop. Like this is also something that you could do. It's not very useful here for now, but there's another nice thing here called the frequency penalty. There's also presence penalty, but they are similar. Frequency penalty, as you can see in the description here, means that how much should we penalize new tokens based on their existing frequency. What does that mean? You may want to prevent the model from repeating stuff. So you just increase this penalty. This is basically a function that is applied that would try to prevent the model from repeating the same thing so that it can generate more stuff. Like here, say hello 100 times, but we set the penalty to a high thing. Say hello 100 times. What do you expect to happen?
Excuse me? Can you hear me?
Yes, I can. Sorry.
Okay. What's the difference between like frequency penalty and temperature? Like they
So the
both
thing
like
is, frequency, from what I remember, only talks about either it is already there or not, but presence, but frequency also counts, it takes into account the number of repetitions, if I remember correctly. I hope I'm correct. Yes, yeah, it's also here. So presence means they have appeared or not, it's binary. Frequency means how many times they have appeared. Like, you know what I mean, right? So presence, even if there's one time used hello, it will penalize. But frequency does not penalize like up to maybe 10 times. It would penalize the more you use it. So it's just different in that direction. Yeah.
So what's
Sorry? Top P is again like the top P or top K, I told you. Like what's the what threshold of the probability that it should take? I don't have an example that here can show what the effect of top P is, but yeah, you know what I mean, right? In the example of the weather is cold, you can increase the top P to, yeah. So here, say hello 100 times, just hello. What do you think would happen if I have a high frequency penalty? I think the answer, of course, is that it would not say hello 100 times because the frequency penalty would not allow it to. But the thing is, would it, let's see what happens. Interesting. So it tried to write hello in different ways, which is very interesting. So these are actually tokens that are similar to hello in the space. Then it tried to use weird stuff and then wrote hello repeats without changing the structure, hello like this, low L, and break HTTP. And then it said, shall I continue? So you see, it tries to output the most probable next thing, but the thing is, apart from the word hello, the rest have very low probabilities. So it has to write something. And that's why the words are weird. Because when it wants to continue this, really the most probable one is hello, but the penalty does not allow it to, so it generates something random. So we saw how GPT can generate continuation, right? But how can it solve exam questions? How can it do weird things that's how can a model that just generates the most probable next token be such useful in answering questions? That's what we call it emergent behaviors. Researchers found that when we, actually OpenAI found that when we train GPT models in a large scale on a lot of parameters, some behaviors that were previously thought only humans have them are beginning to surface in GPT, which is very nice. Let's see. I mean, you know these behaviors, but now we want to also see them together. So, first of all, back to sequence. Just apart from GPT, we can train transformers to do tasks for us, like for example, do translation. We can train a sequence model to translate from English to French. We can train a sequence-to-sequence model to summarize a text, right? This is what you could do already. We can also train a model to do all of them in the same time. The example is T5. You just specify the task, translate, and then the thing, and it would know what to do. So you can train one model on different tasks at the same time, if the model is big enough. Any questions, right? I don't go into details, right? But you can train a model to do multiple tasks at the same time as well. This is what people did before GPT. But the very interesting pattern is that GPT was actually able to do this without being trained to. Like they just trained GPT to continue what is on the internet, and it was able to translate the stuff. It was able to summarize text, which was pretty exciting. We know that large language models, as they call it, LLMs, like GPT, are getting bigger and bigger, and they are emergent behaviors. So let's see the example of GPT-2, which was the first model to show some of these emergent behaviors. Write the capital city of each country. Germany, this is what I wrote myself. Germany, Berlin, France, Paris, Italy, and then I asked the model to generate the continuation. What is the most likely continuation here? You agree that the most likely is likely wrong, right? So in a sense, the model is answering our question. Do you agree with me? So it's not only generating a text, it's answering my question. However, the way that I did it is that I wrote some examples so it sees the pattern, and then it knows after each country, the most probable word to come is the capital. So here, the most probable word is not the capital. However, it's not also very capable because GPT-2 was a weak model. You can see an example here. Switzerland, Zurich. Why do you think this happened? Why it didn't say Bern? Do you have any ideas? Why GPT-2 says thinks the capital of Switzerland is Zurich?
Talked about
Exactly. Zurich is a more famous city, right? In like people, I think talk about Zurich more. Like there's the ETH there, which is pretty popular, and like I don't know, FIFA and everything. But there are a lot of things in Zurich. So I assume there are more articles co-occurring in Zurich and Switzerland. So based on reading the content, it has recognized that Zurich is actually the capital because it doesn't really know what is the meaning of capital. Here it says, okay, the same relation of Germany and Berlin, France and Paris is the same relation of Switzerland and Zurich because they occur more. However, when the models are bigger, they see lots of more articles, and this would automatically get solved over time. But this is a perfect example of hallucination. Maybe you have heard this word. Hallucination means when the model confidently says something wrong. And that happens a lot in GPT. Even now, like the model confidently tells you, like when you ask who is person X, it might tell you stuff about person X that don't exist. Like this. So the models tend to hallucinate and generate wrong facts with confidence, as you can see. We call this in-context or few-shot learning. What is few-shot? We are giving different shots, like this is one shot, two shots, and then we are asking it to continue. This is the way of asking LLM to do a stuff for us. We call it in-context or few-shot learning. There is another way to do zero-shot learning, which means you don't give any example. Like here, the capital of Italy is, and just pick the next word that would come. We didn't say Germany, Berlin, Switzerland, Bern, Italy, what? We didn't say the examples, right? So this is another way. We call it the zero-shot way. Any questions? All right. So here, the generation is not very nice, right? You see the capital of Italy is wrong and the capital of the world is wrong, is it? The city of the Rome is capital of this. So we are only considering this token. So that's the zero-shot approach. However, this is just for simple examples. People found that actually GPT-2 is very bad at these kind of things if we make the example more difficult. Let's see here. GPT-2. What is the code to print hello world in Java? Answer. The code to print hello world in Java is, this is not the code that you wanted, right? Java.language, print Java.language, what's this? This is not the code. But you ask the same question from GPT-3. The code to print hello world Java as follows. Public class is the full code, right? So you see here, when the model size increases, the zero-shot abilities of the model improve. And there is no definite answer to this. Why? Why, when we increase the size of the model, it somehow improves in zero-shot answering? By zero-shot, we mean we just give the question and it gives us the answer. No one has found a definite answer to it yet, I think. But that's how it works, and that's how GPT works. Any questions? So this is the part that I can't answer you why, but it's gonna work, like it's working. But we can definitely say that the size of the model has an effect. Like when you go from GPT 2 to 3, you see how much it improves. The quality can differ, especially in difficult questions, and that's why we do prompt engineering to find good prompts to ask around the model. Again, there's another example here. Write me the code to train an NLP emotion classification LSTM-based model using PyTorch. The answer of GPT 2 is, I'm not sure what to call it. I'm not sure what to call it. Sorry, this is trash. But here, GPT 3, it gives us the whole code, actually, with torch and everything. So, yeah, maybe the code is wrong. Maybe there are issues. GPT does not give everything correctly, but when we increase the size of the model, it's going to improve. Okay, we have already played with the parameters. There's another emergent behavior. So first of all, any questions about few shots and zero shots? All right. This is the less technical part of the presentation, I have to say. Like, this is what you all are used to. There's another emergent behavior. And then I will just say quickly, when I finish this, I'll just say quickly what has been done in the world of LLMs in the past year, like in very new stuff, and then we'll have a goodbye. So imagine this example on the left. There's this question that you want to answer, like there's a question example and the answer. In the cafeteria are 23 apples. If they use 20 to make lunch and bought 6 more, how many apples do they have? What's the answer? What's the answer? 23. 20 to make lunch. I think they have 9, right? They should have 9. Yes. Yes, 23 minus 20 plus 6, right? So, however, if you prompt it to one of the early GPT models, it would say the answer is 27. Why do you think so? Why do you think it got this question wrong?
It's bad at math because like the next token prediction, like it just don't know how to calculate.
Exactly. Both your answer and your answer will be the same thing. You're just predicting the next token, and 27 does not mean anything to the model. So how should it think? It doesn't calculate, right? It just predicting the next token. So in many tasks, the model would not work. However, there was this idea that asking the model to think before answering. Like this. It's like here, it answered the cafeteria had 23 apples originally. They used 20 to make lunch. Until here, there's no calculation. So they had 23 minus 20 equals. Here, there are a lot of sentences in the internet that says 23 minus 20 equals 3. So when they want to predict this token, really the most probable token is the number 3. Did you understand what I mean? So if you ask the LLM to think, ask the model to think, it would indeed pick a correct one. Again, continuing. They bought 6 more apples, so they have 3 plus 6 equals. Here, I think every textbook of elementary school has this sentence in it. So the model knows the most probable token after 3 plus 6 minus equals is the number 9. So it's just right, and that's just the answer. So without any calculation, without summing up numbers, just by thinking, the model was able to give us the correct answer, which is very interesting. And we call this behavior chain of thought. So usually ask the model to think step by step before answering, and it would give us more correct answers. And there was this new thing, maybe you have heard the O1 model of OpenAI or the new model of DeepSeek. They actually integrated a kind of chain of thought into the model itself. So each time it wants to answer something to you, it first thinks and then answers to you, so that the answers are factually correct, or at least more correct.
Is that in the weights of the network or is it software engineering?
It is so the capability is somehow in the weights, because actually smaller models like GPT-2 can't do this at all. It started, I think, from GPT-3. Like GPT-3, I think, if I remember, was the first model that could have done this in practice. So you need to have models that are capable of doing this, but asking, let's think step by step, is just something you add to a prompt or you add to an example. So that part is the software engineering. Yeah, you don't change the model necessarily, but the model should be strong enough to be able to do this. Like it should know that 3 plus 6, the most probable next token is 9.
One could just be GPT-4 plus.
Yes, but so they do some RLHF stuff that I will get to it. They do some extra steps on top in addition. But in practice, yeah. So in practice, the basic definition that will fit into the content that you have today is that it's somehow first thinking, we say generating thinking tokens, and then using it to generate the answer. So in a sense, yeah. That's what I wanted to say. So it's not enough still all of this is not enough for a useful chatbot. We need to align the output with the human expectation of a nice output. Let's say this example. If you want to ask I want to make a purchasing decision, and I ask GPT, what are the differences between a Mac and a Windows PC? I want to check one. Okay, GPT-2 is trashier. The Mac is a very good computer. It is a very good computer. It is a very good computer. Okay, it loves to say Mac is a very good computer for some reason. So, maybe that's true. I don't know. Let's see. But GPT-2 just repeats the same thing again and again. However, here, when you ask GPT-3, what are the differences between a Mac and a Windows PC? It gives the answer. However, it's not in a very well-formatted structure. Maybe you expect better from GPT. And actually, if you ask GPT, like one of the newer GPT models, like ChatGPT, you see it's very better structured. Like, so what they did, which was actually I think first done by OpenAI, was something called reinforcement learning from human feedback. I won't go over the details, but they basically started from a base model. They trained another model to reward a text based on how it aligns with the preference of humans. So how they did it, they showed a lot of text to two humans and asked them to rate them, which one is better and which one is worse. And they used them to train a model to pick which text is better and worse, and then use all of those training to fine-tune or to help to train GPT to output text that people like it better. And that help to text that people like it actually better. That's why also GPT loves to usually please the users. It always loves to agree with you and this kind of thing, because it's trained to be like that, right? So this is the whole idea of LLHF. I won't go into details because that's, I think, for like a lecture on itself, but the idea is that LLM generate text, humans give feedback, and the model improves iteratively. Did you get the idea? So we get humans into the loop. Any questions? It's just for the model to generate things that we like as humans better. And all of them led to how ChatGPT is now working now, as you can see here. There are downsides of doing this. Maybe you have heard about the controversy of the word delve. So people did a study and found the number of words, the word delve is used in published papers has jumped after 23 for some reason. And they found that because ChatGPT loves to output delve and people are using ChatGPT to write their papers. So basically in the published papers, there are a lot of more users of this word. And the reason was that seemingly in the place, one of the places that they did the RLHF training, in that culture, people use the word delve much more. So they rated the text that they use the word delve with a higher rating. So GPT learned that delve is a really nice word to use and then try to use it over and over. So you can see there are downsides on how LLMs are trained. There are things that we can't control and depend a lot on what humans label and train. And thus, it's always, we need to be careful on what they output. Just wanted to give you a nice example here. Any questions? Perfect. So you're already 6:28. I want to finish 6:30. So we have 2 minutes, but maybe let's finish this slide and then we can go. So LLMs, large language models, or as we call it, the GPT or anything, are very powerful, right? They can give us, they can even do classification for us. Like you can ask GPT, is this a sad or happy sentence? You don't need to train the BERT anymore these days. You can ask ChatGPT or do a lot of very interesting stuff with GPT. So they have very high zero-shot performance, few-shot performance. They can do chain of thought. There are models that coming every day that basically are beating benchmarks over benchmarks. People are coming with new benchmarks. Is NLP solved? It's still not solved, right? Of course, the answer is no. Why? Models, of course, LLMs, ChatGPT, are pre-trained. They have a high zero-shot performance. We don't necessarily need human data set annotation anymore. We need less, because GPT can itself learn a lot, and we don't need a human to sit and label everything. Human labor is decreased. And LLMs also have natural human-like interactions. So we can use them in chatbots or even in place of people in customer services or places like that. However, there are still downsides with LLMs. They have low controllability. We really can't control them well, I have to say. This is what a lot of people say. Like, we can't make them really easily generate output from a certain range, as they can easily go around guardrails. basically OpenAI and other companies have tried a lot to prevent guardrails from prevent LLMs for doing stuff, but you can always find a pain around them. So they are not very controllable. They are still prone to hallucination. They confidently predict the token, which is not the correct token to predict, just because it's the most probable token. They have limited encoded personalization or state, and you should tell everything that you want. They don't have a memory like an RNA or things like that. You should tell everything in the long prompt that they have, and it can lead to long prompts and possibly not paying enough attention to parts of the prompt and a lot of problems. And finally, they are also very expensive. They have a high inference time and cost, as well as high training time and cost. As you may have heard, like OpenAI is raising money, a lot of money to just train models, and also it can have a lot of consequences for time and cost as well. So still, we can't say NLP is solved, but we are moving in the direction. So these problems are still problems that exist, but maybe in a few years or maybe even less, depending on the progress, we will have artificial general intelligence as they tell us by having LLMs. This was just a thoughts slide. Any questions? All right.
I have like more
Yeah.
technical question.
Yes. Yeah. Sorry. This was the ending part was a bit less technical because I just wanted to say that. But yeah. Yeah. Continue. So the slides are finished actually. So now we are the questions. Yes.
Yeah, like for instance, we just first pre-train our model on the whole internet, and then we need to apply supervised fine-tuning. Is it just like the same as we do with all models? We just like decrease the learning rate and just like keep training on the question answer pairs, or do we need to apply some, I don't know, customized mask, like like this attention mask
So you
when
freeze
we
the body, right?
Hmm?
You can freeze the body and just train the head, and that's possible. But you
Is
don't
it
need to provide any kind of mask. Basically, the models, including BERT, usually understands pretty well what do you want to do. Like if you just use the output of the CLS token for your classification task, for example, you don't need to do any kind of masking. It will automatically recognize and be able to fine tune. They are strong enough to do that, actually. So I don't know.
Okay.
But
So
yeah.
So in like GPT-like architectures, I just like freeze all of the weights except my MLP and then do the question answer fine tuning as like I did pre-training,
Yeah,
right?
exactly. You just keep ahead, keep a set of last layers, and you can freeze the rest. And it would ideally, like it depends also on the situation and how you train it and all layering rate and everything. But ideally, with just transfer learning, it should work. Yes. Yeah.
Okay, got it. Thank you.
That's the whole idea. And also, there's another thing that I didn't discuss today, but there's this new concept, maybe just say quickly to everyone, called LoRa, which is now pretty much used. So they provide a low rank approximation, like this out of scope for today. But the idea is a better version of fine tuning in which we have a parallel branch to the blocks of our model, and we just train those models, which are smaller, which are lower ranked matrices, which are smaller. We just fine tune those in order to fine tune the whole model. So you can search for LoRa. It's a pretty newer approach for fine tuning models such as GPT or LLMs, and you can also use that for fine tuning your models. I think these days it's actually used a lot. Sorry?
It's the same.
So it's way more efficient. Like the accuracy, of course, depends on the task and everything you should run, but it's more efficient, usually run faster, and also takes much less space because you only keep the LoRa weights. So you can have, for example, a big model stored, we call it the foundational model with a lot of weights, and then keep a set of LoRa weights for different tasks you want the model to do. Each of them is just fine-tuned version of the model on a different data set. Yeah. So, any questions? Yes.
Just organization, I took notes that this lecture would have been about deep learning for audio.
Yes, so it was. I posted in Discord for this confusion for this morning. It used to I wanted to be for audio, but they changed I think the plan. So I think I just posted this morning that is for NLP. So they just announced the plan change.
Okay, so all the lectures swapped. Just
Yeah. I think tomorrow either tomorrow is audio, then it's CV or vice versa. I don't remember exactly, but yeah, maybe you can ask in Discord because those are I'm not presenting. It was my last, so those are for two different people. You should ask which one is which because they just told me right today that this one is NLP. So yeah.